In this video, we're going to take a look at the second half of section 8.2. So last video was mostly about trying to prove the Pythagorean theorem. We did one or two examples with it. Today's going to be more so, or this video is going to be more so looking at the way that we're using Pythagorean theorem to solve problems. So I'm going to start this video off with the end of what I wasn't quite able to finish in the last video. And so we had these two right triangles right up next to each other. We're supposed to solve for the length of AB, which is x, but in order to do that, we had to first solve for the length of BD, which we figured out was 4. So then we just set up another Pythagorean theorem using 4 and 7 as the legs and x as the hypotenuse. So 4 squared is 16, 7 squared is 49, and in this case, you just add those two together, so you get 65 equals x squared. And then in order to solve for x, you've got to square root both sides. So you would get the square root of 65 is equal to x. The good news here is that 65 isn't really simplifiable when it's underneath the square root. If you break 65 up into its two parts, it's 5 times 13, and that's it. There's no groups of 2 that we can pull out of that square root, and so we can just leave square root of 65 as our final simplified answer. All right. Now, as we go along, we're going to take a look at a few different questions that will ask us to kind of have to visualize a little bit and to kind of see where are we going to use Pythagorean theorem in a diagram that maybe doesn't give us a right triangle right off the bat. All right, with this problem, go ahead and pause the video. Try to solve it in your notebook. You might want to draw this picture out and actually play around with maybe adding a line into the diagram to see if it will give you an opportunity to solve. Now I'm going to move forward with the solution here, and one of the things to learn from this problem is that the thing that you're looking for instance, in this case we're looking for the length of DC. It may not be immediately solvable, and it may not be obvious how to solve it. In the previous example, we were given 2 right triangles, and so it was pretty obvious, okay, just use the right triangles and solve. But here, this is actually a trapezoid with right angles, but there's no triangles given. So therefore, if we're going to solve this question, we have to create a triangle ourselves. Okay? Now there's a couple different places you can create a triangle. Like you could create a triangle from A to C, and you could solve the distance of AC. But the problem is that the bigger triangle here is not a right triangle. And so then trying to use something from that triangle to solve for x is not going to work, because Pythagorean theorem only works when you have a right triangle. The same problem is going to happen if we draw from B to D. You'll get a right triangle, but 2 of those right triangle sides will be unknown, and you'll only know one of the sides. So the right place to draw a line in this diagram is actually straight across from point A. And this line will be parallel to the line to side BC below. Now what this line will do, assuming that it's perpendicular to this other side, it will create a rectangle over here. And we know that rectangles have opposite sides that are congruent. So now we know that the little length here from C up to this intersection point here is going to be 18. We also know that this length here is going to be 20. And now we can create a new variable, we'll put it as y, to solve for this distance right here. We have now created a right triangle, and 2 out of the 3 sides are known, and so we can actually use Pythagorean theorem. So 20 is a leg, and y is a leg, so we'll do 20 squared plus y squared, and then 29 is the hypotenuse. So 20 squared is 400 plus y squared equals 29 squared. That is 841. Then we can subtract the 400 on both sides, and we get y squared equals 441. In order to get y by itself, to get rid of the squared, we have to square root both sides. Now there are times where you'll be doing the square root of a number, and it's a really big number. You may not know that this number actually square roots to be an integer. 441 is a perfect square. This square roots to be exactly 21. Now this means that y is 21, And so then to actually solve the length of DC, you have to add 21 plus 18 together, and that would give you 39. There's going to be a lot of problems we solve in this chapter that are kind of like this, where you have to split a shape up. You have to add a line into the diagram in order to get the right triangle that you're supposed to use to solve a problem. And so part of the skills we're learning is to learn where to draw those lines, okay, and when to draw those lines. All right. Now, one thing you might have noticed that was kind of cool about that last example was that in this upper triangle right here, all three side lengths of the triangle came out to be integer values. One leg was 20, one leg was 21, and the hypotenuse was 29. No nasty square root answers to leave in there. And so there's actually a name for this when the three sides of a right triangle work out to be integer values. We call these Pythagorean triples. And there's a few really, really famous ones. The most famous one that I can think of is 3, 4, 5. We actually saw that one earlier in the example here. We had a leg of 3, we had a hypotenuse of 5, and then when we solved out for the other leg, it ended up just being an integer, and it was 4. So what you can learn about the Pythagorean triples is that some of these are easy enough to memorize, and you can sometimes solve problems just by memorizing these Pythagorean triples. The cool thing about these Pythagorean triples too is that they come in any scaled factor. So for instance, if you have a triangle 3 and 4 and 5, you could double all of those lengths, and you could guarantee that a right triangle could also have a 6, an 8, and a 10, with the 10 being the hypotenuse. Or you could triple them and have a 9, 12, 15. Another famous one is 5, 12, 13. So again, you could double that. You could have a side lengths of 10, 24, and 26. Or 15, 36, and 39, etc., etc. And then the last two that are kind of famous are 8, 15, and 17, and 7, 24, 25. Now, I'm not going to make you memorize any of these Pythagorean triples, but what I will guarantee you is that at some point in your solving process, you will see these. And so if you do memorize a few of them, it might make your work go a little bit faster. You might just look and see, oh, I've got a leg of 3 and a hypotenuse of 5. I know that the other leg has to be 4. And you just know it. You don't even have to solve it out. But it's up to you how much time you want to put into memorizing these. Okay. And then there's also other Pythagorean triples that I'm not listing down, and those are ones that, I mean, again, you could go out there, you could memorize a list of them if you wanted to, but I'm not going to spend a lot of time on that. I think the obvious question that kind of comes out of this discussion of Pythagorean triples is this idea that instead of having a triangle and knowing that it's a right triangle and then using that to solve one of the sides, what if you just have 3 side lengths and you're asking yourself the question, will these 3 side lengths come together to form a right triangle? And so that actually is what's called the converse of the Pythagorean theorem. The question of turning around the Pythagorean theorem on itself. So let's start off with a simple scenario. Let's say Chandra has boards of length 8 feet, 4 feet, and 5 feet. The question is, can she create a right triangle with them? So in order for a right triangle to be created, you have to have side lengths that match the Pythagorean theorem or that work in the Pythagorean theorem. So as you're looking at these 3 side lengths, there's only one of them that could be the hypotenuse. So if we're creating a triangle here, obviously the 8 would have to be the longest one, which means the 4 and the 5 would be the smaller ones. Now, if this is going to be a right triangle, we should be able to plug these values into Pythagorean theorem and have them work out. So when you're doing the converse of the Pythagorean theorem, you're doing kind of a comparison. You're always putting the longest side by itself, acting like it's the hypotenuse, and then you're doing the 2 shorter sides by not by themselves, but together. Like, so you're doing the shorter side squared plus the other shorter side squared to see if it equals the longest side squared. And here we're doing a question mark. We don't know if it's going to work out. So if Chandra does this calculation, she's going to put 8 squared on one side, and then we'll do the two shorter sides on the other side. 4 squared plus 5 squared. 4 squared is 16, 5 squared is 25, and 8 squared is 64. If you add 25 plus 16, you get 41. And so we can see that these are definitely not equal. So what we can say for sure is that this is not a right triangle. So then that begs the question, what kind of a triangle is it going to be? So to answer that question, we need to take a look at a few different kinds of triangles. So let's go forward a couple slides here. Now, the one in the middle is a right triangle. So this one's obvious. We know for a fact that a squared plus b squared would have to be exactly equal to c squared. But take a look at the one on the right. This angle right here has clearly gotten to be obtuse. It's gotten bigger than a 90-degree angle. Now, if you notice, the length of A and the length of B have not changed at all. The only thing that happened between A and B was the angle got bigger. But what happened to the C length in order to allow that angle to get bigger? You can probably see that the C length had to get bigger to accommodate the bigger angle. And so what that means is if we were to do a squared plus b squared and compare it to the length of c squared, in the obtuse triangle, the c squared would be the bigger part because that c side had to get bigger in order to allow for the obtuse angle. And a very similar thing happens in the acute angle. If you take angle C and you make it be like you make it get smaller, so it's an acute angle, C had to get shorter in order to allow for that to happen. So if you try doing Pythagorean theorem with an acute triangle, you'll find that the a squared plus the b squared actually ends up being bigger than the c squared. So we can use this idea to tell whether a triangle is right, acute, or obtuse if we know its 3 side lengths. You can pause the video and take some time to copy that into your notes. I'm going to move forward into a couple examples. So let's start with this one. We don't know if it's right, acute, or obtuse, but we do have the 3 side lengths given. We know that 21 would be the hypotenuse if this is a right triangle, so we can set up our equation. And I'm going to put a question mark because we don't know if this is going to work out. So 21 would have to be squared by itself, which means the 14 squared and the 15 squared would have to be on the same side. Now, if you do 14 squared plus 15 squared, you get 421. And if you do 21 squared, you get 441. And so we see that the c squared side is the larger side. That means that the hypotenuse got bigger than it would have been if it was in a right triangle. That means this is an obtuse triangle. Let's do one more example. In this one, it's kind of difficult because it's hard to tell which one is the bigger side length. You can use your calculator, and the calculator will tell you that this is about 17.9. So that one is the largest side, which means we need to compare 8 squared and 16 squared. We need to put those together and see if it's larger or smaller than 8 square root 5 squared. So 8 squared plus 16 squared comes out to be 320. And in your calculator, you can do 8 square root of 5 and then square that. You might need to put parentheses around the 8 and the square root of 5 before you square it. And that comes out to be 320 as well. So in this case, we see that they actually are equal to each other, which means that the Pythagorean theorem worked, and this is a right triangle. All right, so that's how to use the converse of the Pythagorean theorem, and then we're just going to solve a bunch of problems with both the forwards direction and the backwards direction of the Pythagorean theorem. So go ahead and work on your independent practice for 8.2.